You know, this problem's still the same idea. I drew a different set of level curves here. I put a point A and B on there. I put the Z values to let you know which way is uphill versus downhill. And I ask you to sketch, you know, a couple of gradient vectors of the points A and B. So just, you know, same idea, just a different looking set of little curves.
It's open between now and next time.
And one thing I did do for test 3, the polar problem is manageable this time. A little bit easier. So you should be able to integrate it pretty straightforwardly.
Okay, we just have to set it up.
Well, if you set it up, that's one thing, but I actually typed the words. I mean, I use this as my guide. I actually added the words, I do want you to evaluate it this time, so that way you at least evaluate. You've been tested on evaluating one polar interval. But the transformation into polar is the integrand turns into something a lot more easily to integrate than that. Okay. So I really just took the original copies of what I have for test 1, 2, and 3 and just changed to different numbers. Okay. So like on test 2, the z-coid problem about the z-coid, you know, starting at 8 meters above and having horizontal initial velocity, that's still a z-coid problem. I think I changed it to 10 feet above and it's going, you know, a different horizontal velocity and its acceleration is a different function, but it works the same way. So if you got it down pat on how to work the problem, just, you know, apply it to the different numbers that I changed it to. So those tests are in the testing center from now until next Thursday. Try and take it as soon as you can, because this time next Thursday, the first half of next Thursday's class will finish the material that we want to do, and the last half we'll go over, you know, how to, you know, get your notebook in order, because test 4 is open notebook. So you'll want to, you know, as you're going through the homework, maybe, you know, use some post-it note tabs to sort of be able to easily locate certain kind of problems, and even write little things over there, like here's how to do this DS line interval, here's how to do a parametric surface or something like that, so that way you can easily reference anything that you need to. Anybody, I know a couple of people have mentioned wanting to take it in the testing center. Anybody else insist on wanting to take it? I mean, insist, not that it's a bad thing if you insist, but if you want to take it in the testing center, you have that option. Because I know it's finals week, and so you probably.
Where else are we going to take it?
Well, it's originally going to be in here.
For the retest?
No. This is the test 4.
Okay.
This is test 4. Sorry.
So
No, the retests are in the testing center. I put them there today. They're there through next Thursday.
Are you going to cut us off right at like the time limit?
Oh, you mean for the second attempt test?
No. Test 4.
Oh no, if you have to stay late, I'll just bring a movie and watch it. I've done that before. Totally put my laptop, put my earbuds in, and sit there and watch Raiders of the Lost Ark when I take a test. Shamelessly.
When's the final actually scheduled for this class?
The time slot, a lot of us, is Tuesday, May 5th. Technically it's 6:30 till 8:30 or something like that, but if we start at 6:15 just like class time. I'll get in here at 5 o'clock that night, an extra hour and 15 minutes early, so if there's any last minute questions you have, anything you want to go over, last minute bells and whistles, we can do that.
And if we wanted to take it in the testing center, I assume it would be available until...
I almost say Wednesday. When did you want to take it, Danielle? You can take it on Wednesday? Test 4? Okay. I like to get it done by Thursday because it's grades are due Friday.
Okay.
Any other questions? You may come up with more questions, so feel free to email me if you do think of something that wasn't covered. Please, again, double check to make sure. I've contacted a handful of people like Dax and some others who don't attend regularly to make sure that they're going to be retaking the right test. So if your name is not up here, then either you've already let me know that you don't want to take a test over, or or you're okay with the test grades you've got. So I just want to make sure before you leave tonight, let me know for certain. So I'll make sure I have the right kind of copies in the testing center. And those retaking test 1, give me until. Are you going to take it tomorrow?
No.
Danielle, you're probably taking it tomorrow. Maybe. Okay. So there's a screw up with test 1. Only test 1. Simply because there are these images that are on her copy that I left space for when I made my document, but I completely forgot to go back and actually draw these vectors. I forgot to draw these vectors. I forgot to draw this semicircle. I forgot to draw this vector. I do have the surfaces on there, so there's a matching problem for the surfaces, but I went ahead and fixed it about half an hour ago, so the copies are ready, but the ones that are in there now, don't take them. I'm gonna have to go replace them tomorrow morning at 9 when they first open, so I'm glad no one's actually taken.
And the retest,
Test one's retake.
the retest will be available in the testing center until Thursday of next week, correct?
This time next week, yeah. Yeah. Any questions about the retaking process? Okay, any questions about test 4? Probably too soon because we're still going through the material for test 4, but it's just going to be on our final exam time slot that Tuesday, the day after Star Wars Day, May the 5th. And I'll say we'll begin at 6:15. If you need to stay till 9:15, we can do it. Okay, so. All right. Oh, and I told you the answer keys to the test are on D2. I told you that. I know I'm giving you a lot of redundant information, but I just want to make sure I get the right information out there to you. Do you have any questions on what we've done so far? Triple integrals and XYZ coordinates. Or triple integrals and spherical and cylindrical coordinates. Line integrals. Okay. Have you had a chance to do any homework? This is when the notebooks come out.
Don't make eye contact with me. Don't look at me directly.
I understand. It's the crunch time of the semester. You've got deadlines. You've got papers. You've got lab reports. You've got Chinese vocabulary to memorize. I understand. It's the hectic time of the year. Just don't let go just yet.
I'll sell it for you.
As you're doing the homework, you might want to keep in mind test 4 is open notebook. So try to keep organized and keep everything sort of in order. And if you have a really thick notebook, I mean, all you really need is the stuff that we're doing for this test. I mean, you can put anything in there. If you need a table of integrals, boom, I can't police that, no problem. If you need a unit circle, boom, put it in there. I can't police that, okay? I'm not going to actually look at what your notebook has in it. Although, if your notebook has an iPad or a laptop in it, we have issue with that, all right? So by notebook, I mean spiral bound, binder, like that, with the papers, your notes. You can print off the scan notes that I put on D2L. You can print off the solutions to the homework problems that I put on D2L. So you can have whatever you want. Clipboard, whatever. You're a clipboard man too. So
working on or studying.
Whatever you want to have in the notebook that's, I guess, relevant to the test. Shakespearean sonnets, whatever. Just I don't want you to have access to anything digital or laptops or anything like that because that's just.
So no access to calculator?
No, you can use your calculator. That's for sure. Yeah, if you need it. So.
Do you mind if we listen to music while we're doing?
Earbuds.
Yeah.
Okay, as long as you have your. Do we have to listen to it too?
No. No, it's.
No, you can make it through without music.
Yeah.
Well, I'll have my earbuds on up here if I'm watching a movie, so I can't actually tell if you're listening to music or not. What is your music of choice that you like to listen to?
I like to listen to classical while I study physics. I like to listen to traditional Chinese while I study Chinese. I like to listen to bonobo while I'm doing chemistry. And
I just like to pop in some John Williams. Any John Williams soundtrack from between 1975 and 1989. That's just anything you did. You know John Williams, right?
Try to listen to whatever type of music.
He's the guy who did all the orchestra music for like Superman, Star Wars.
Very good.
Yeah, it's just
London
big pop
Symphony Orchestra.
kind of composer, and so all those Spielberg movies from the 70s and 80s, the E.T.
It's like a natural study aid.
and Schindler's List and Harry Potter soundtrack. He did those. That
Indiana Jones.
Indiana Jones. Home Alone. Close Encounters of the First Kind. Jaws. He's the guy who gave us. So anyway, all right. So without any further questions or John Williams references, we'll go ahead and pick up where we left off. So we've done the triple integrals in XYZ coordinates and in cylindrical spherical coordinates. Then last Tuesday night we covered line integrals, the 3 different types of line integrals, the DS type that has that square root expression, the F dot dr type that makes a dot product, and the dx dy type. Every single type, no matter what you do, you're always going to have a parametric curve that defines your path. You replace the x's and the y's and the z's with their parametric equations, and then depending on what type it is, again, keep those 3 distinguishable, so that way you can make sure you're evaluating the line integral the right way when you're doing it on the test. Tonight, we're kind of recapping that to begin with. I'm introducing this topic by evaluating an f dot dr type of line integral for this vector field along these two curves. And if you want to see what's kind of unique about these two curves, this one, that path starts for t equals 0, you get 0i and 0j, so you start at the origin. And then at t equals 1, you get 1i and 1j. So it's a direct line segment that takes you from the origin to the point 1, 1. All right. Now this one is a little loopier. I may actually have to graph that one out. Your I component here is t squared, your j component is t to the 5th. So I'm going to switch to parametric graphing mode. Have y'all done the parametric graphing line here? I know Beth's not a big, calculator fanatic, but it's kind of handy for certain vector functions to see what the parametric curve looks like. So you don't have to do this. I'm just wanting to see what this particular curve looks like. So I switch to parametric mode, and my x equation is t squared. My y equation is t raised to the 5th, and my t values are from 0 to 1. So then if I graph this out, okay, well, let me zoom in a little bit. Let's draw a box around it. Okay, so it's kind of like almost parabola-ish, that path that goes from 0, 0, and by the time you get to t equals 1, you are at the point 1, 1. So it traces a path that goes from the origin to the point 1, 1, but it looks something like this. Okay, so almost kind of parabola-ish, but see that 5th power makes it a little bit loopier. But the main thing I wanted to illustrate is to let you know that these two paths, they're different paths, but they still take you to the same 2 points. Okay, they still connect the same 2 points from beginning to end. So if we evaluate f dot dr along this path, so to kind of recap, this would use x equals t and y equals t, 0 to 1 for your t values. So I need to take my vector field. My vector field is defined as 2x plus y for the I component. Do you remember what you do with the x's and the y's here? Same thing you do with the x's and the y's for all 3 types of line integrals. Any use of x in either the line integral's definition formula, the function, the integrand, whatever, any use of x, you always replace it with its x parametric equation. And see, even though this is a vector equation, this I component is still the x half of the parametric pair. The j component is always the y half of the parametric pair. So these are both the same graph. Just sometimes you see them represented in vector equation form, sometimes you see them in parametric form like this. Just like this one over here. This vector equation is the same thing as the parametric pair x equals t squared and y equals t to the 5th for the same span of t, 0 to 1. Okay? So when you're setting up an f dot dr type of line integral, you take your vector field that you're given in the problem, every use of x you get to replace with its t equation, so that I component would be 2x plus y. And yeah, I'll probably simplify that to 3 in the next step. Your j component is just x, so that'll just be t by itself. So this is what the vector field becomes when you start applying the parametric curve to it. Replace the x's and the y's with their parametric equations. Then the integrand that you build is just based on a dot product. You do the integrand by calculating f dot dr. And what was dr synonymous with?
R prime.
In other words, the same thing as r prime. So f dot dr is the same thing as doing the dot product of f with r prime. But you only do the dot product after you've made all these t replacements for your x's and your y's. So the dot product of f, which I've now turned into 3ti and tj, I do its dot product with r prime for this particular path. So r prime is just 1i and 1j. Both of your components are just linear t, so that first derivative for each one takes you 1 each. So this dot product gives me 3t plus t, 4t. That's your integrand. So when I set up this line integral for f dot dr, it turns into, and that's supposed to be a C, it looks like a 0. It's the line integral over the curve C of f dot dr. You actually have the definite integral limits coming from where? Do you remember?
0 to 1.
0 to 1, the same restrictions on your t. The integrand is 4t dt. That's it.
dt.
Because every one of these line integrals turns into a t variable integral, whether it's the ds type or the dx dy type or the f dot dr type. And then this integrates as 2t squared, 0 to 1, so you get a value of 2 for this particular line integral. Which, if you wanted to kind of tie that in with work, remember the application aspect of the f dot dr type is I don't have the graph of the vector field overlap here, but if I overlap some of the vectors in this field with this paths graph, then there's a total amount of 2, whatever your work units are, if you want to call it joules or foot-pounds or newton meters or whatever, 2 work units done in moving a particle along that path through this particular vector field. Okay. Now, if the path changes, should the work change?
I think you're going from
I mean,
0
you're technically-
to 1.
I mean, if you look at it as like a displacement kind of calculation, think of the displacement part about work. See, which path is actually shorter?
One on the left.
The one on the left, the straight line segment is a shorter path. This one, because it's got some curvature to it, you're going a little bit of a longer distance. So you think, if you're tying it in with the notion of force times displacement, if your displacement's longer, you should have a longer value in your work calculation. Making it higher or some larger magnitude. But let's double check and see. So a completely different problem here. Starting from scratch, I want to set up the f dot dr integral for this same vector field. The vector field is still the same, but the path is different. So the vector field changes in this case. You still have 2x plus y being the I component. So since I've got different x and y equations here, 2x plus 1y would actually become 2t squared plus 1t to the 5th. There's my 2x plus y from that I component of the vector field. And then the j component is just x by itself, so that'd just be t squared. And then I want to do this thing's dot product with r prime. So that'll build my integrand. So let me copy my f down. I really didn't leave myself too much room to do this. Okay. So sorry if my writing is kind of tiny. Let me zoom in so y'all can see what I'm writing. So there's my f. I'm dotting it with, again, that's not r, that's r prime. So take that mental derivative as you copy this other vector down. Your I component should become 2t from the derivative of t squared, and then the j component should be 5t to the 4th. You're just doing power law on each one of those. So this dot product, just like this one over here, this dot product becomes your integrand that you actually put in the integral before you evaluate. So in this case, I times I is going to give me distributive property there. That's going to be 4t to the 3rd plus 2t to the 6th. And then plus, now you multiply the j components together, plus a 5t to the 6th. So in this case, you got a whole different looking function for your integrand. It's not necessarily harder. It's just a different path, different x and y expressions, different integrand. Everything is leading me to believe that this should be a completely different value. But I'm probably setting out a spoiler by saying this. 4t to the 3rd plus 7t to the 6th. There's my integrand again. So that's what I want to put inside my f dot dr integral. I'm going to integrate from 0 to 1. You have the same t limits, but you just have a different function now. 4t to the 3rd plus 7t to the 6th dt. Both of those work really well with the power rule, kind of handy. And so you end up with 1 plus 1. You get the same value. The same, I guess, if we're going back to the analogy of work, the same work is done in moving a particle along this straight line path through this vector field that's done in moving it along this path in the same vector field. Doesn't happen all the time. When you just make up a random vector field, just pick up a vector field at random, sometimes you should have different work values for different paths because of the displacement being longer, the path being longer. versus the straight line path would be the shortest distance in 2 dimensions. The unique thing about this vector field is, well, it's conservative. Have you ever heard that brought up in a physics class before? Well, there's the law of conservation of energy, and there's other conservative references. But have you heard the specific conservative adjective used to a vector field in physics? Because admittedly, I've never taken like the magnetism part of physics or the physics where you actually get to use this kind of stuff, the line integrals and the flux integrals and the surface integrals and the integrals that look like this, the integral with the little loop through it and stuff like that. So I've never taken that part of physics, so I'm admittedly a little bit curious to see where conservativity pops up, because it makes me think of the law of conservation of energy. So you think about the amount of work doing in lifting an object just vertically up a certain distance versus the work in taking it up a spiral ramp. If the vertical lift is, say, taking 500 pounds and lifting it 100 feet, so that way that's 500 times 100, that's 50,000 foot-pounds of lift work and getting it up there. If you still take the 500-pound object and you're able to spiral it up a ramp that still brings it 100 feet up, is the work any different?
The
Go
network
further.
isn't any different.
The network is not any different, and I guess that's the major thing, because if you're considering the actual push, the lateral work, that's going to be a little bit different. But yeah, in the whole displacement idea, whether it's a vertical lift or a spiral lift, it's still going to be the same amount of work, the network done. Yeah,
Wouldn't you have to take it further if you're going?
your path's going to be longer because you got that spiral, but still,
The Egyptians showed us that the spiral is the easier way to go if you're doing human
well, especially if you have something cranking the spiral or the screw or even something like that. But and again, that's where I have to admit, being on the outside looking in, I know what it means for a vector field to be conservative mathematically, but I've just never seen it in a physics context. So I just need to take that physics class. Go to Farman's class and just say, look, can I sit through your magnetism class?
Yeah,
Just
yeah.
check this out.
Yeah.
I mean, do you actually see? And I'm sorry, I'm digressing, Danielle, for this video. Do you actually see integrals that look like this in the magnetism class and stuff like that? So you do certain integrals, and maybe in some cases you see a little arrow there talking about the orientation of the path or something
I'm
like that.
taking algebraic physics because I'm having.
No, not yet. Okay, so maybe that's a little bit higher, but that's something we're going to talk about here shortly when we get to Green's theorem. But here and now, within our 4 walls of the context of Calculus 3, certain vector fields have the property that no matter what path you take connecting the same 2 points, you're going to have the same value for your f dot dr integral every single time. This vector field has that property. It's an example of what's called a conservative vector field. If I started at the origin and went, in any path, if I took a spiral path that allowed me to go right here, and I had parametric equations for that path and t values, then I calculated the f dot dr integral, it's always going to be 2, so long as the end point and the beginning point are still the same points. So no matter what path you take, you're always going to get 2 as the f dot dr line interval value connecting those 2 points for this particular vector field. Okay, so here's where that ties into what's called the fundamental theorem of line intervals. Okay, if the vector field you're dealing with is conservative, so since that's the if statement, we need to come up with some way of seeing or determining how a vector field is conservative. Okay, and there's actually a test that you can apply to see if you have a conservative vector field, because if you have a conservative vector field, whew, big relief off your shoulders. All this work becomes a little bit easier to deal with, okay? If you have a conservative vector field, there exists or in other words, if it is a conservative vector field, that means there exists a scalar function, some little f of x, y, like the functions you've been dealing with in Calc 3 all semester. There exists some function of x and y. And notice, this isn't a vector field, this is just a scalar function. But in order for this vector field f to be conservative, there is a function like this that exists, such that when you take its gradient, it gives you the same thing as the vector field. So in other words, a conservative vector field is some function's gradient. So it's kind of like in order to find out what this function is, you almost have to come up with a way of doing the gradient backwards. Do you remember how the gradient was created? Since that was one test away, I'd like to think you do. Yeah, so as a recall, the gradient of, and again, this is a vector, but remember the little f that I'm trying to deliberately write here is cursive. That's a scalar function f. So I'm not trying to say that that little f is a vector quantity. You would do that operation of gradient to the scalar function f, and it produces this vector, partial with respect to x is the I component, and partial with respect to y is the j component. If you have a 3-component vector field, same idea. Then the I component, the j component, and the k component are partials with respect to x, y, and z in that order. So if a vector field is conservative, there exists some little function f like this, such that when you take little f's gradient, it becomes the same components as the vector field. So in other words, going back to this previous example, way back up here, there exists some function of x and y, some scalar function, such that that is its partial derivative with respect to x, and that is its partial derivative with respect to y. Does that give you a rough idea as to how to find that scalar function? Yeah, since gradients created by doing partial derivatives with x and y, and in some cases z, you could take each of those components one at a time and do an x antiderivative for your I component, a y antiderivative for your j component, and a z antiderivative for your k component, and then those should produce something that looks like what your scalar function f is. This function f that I'm referring to here, there's a name for it. A little bit of vocabulary in the statement down here at the bottom. So there exists some scalar function that when you do the gradient to it becomes the vector field. Then the value of the line integral along any curve that connects the point AB to the point CD is this. Here's the line integral we've been evaluating so far tonight. We've been doing f dot and dr type, where you take the parametric curve, you replace the x and the y, you do the dot product with r prime, and then you integrate. Instead of doing it that way, you can evaluate it by taking the scalar function, which at this point I'll call it the anti-gradient. You find this little I mean, it's kind of the idea of what it is. You're given the vector field f in the problem whenever you're looking to find these line integrals, and you want to come up with this little scalar function right here. All you have to do is find out what function that is, and then evaluate that scalar function at the end point of your path, and subtract the value at the beginning point of your path. Does this look familiar? This idea of plugging in the last value first and then minus the first value plugged in last?
Yeah.
From vector length.
Well, not vector length, but
Slope?
not slope.
Kind of slope.
Fundamental theorem of calculus 2. Yeah. Just finding antiderivatives, you take your antiderivative and you plug in the b value first, which, from a to b, a is less than b. You plug the b value in first, your endpoint, minus the a value plugged in last, your beginning point. So it's kind of like that same analogy of the fundamental theorem of Calc 2, but now you're applying it to these f dot dr integrals in vector fields. Okay? So, and there's my version of it. If you know what the 2 points are in your path, you know what your beginning and end points are, then it's always anti-gradient function of the end point minus anti-gradient function of the beginning point. And it's not really called the anti-gradient. Although I like to call it anti-gradient because it kind of tells you how you get it. You have to sort of do the gradient backwards to find this little f function. The proper name for this function f is called the potential function for the vector field. Okay, so since that's what mathematicians and physicists refer to that function as, I'll go ahead and underline that as another vocabulary term. But I'm going to also put, just because I like it, I'm going to put a little AKA down here. I'm going to call it the anti-gradient also, just because it kind of makes sense to call it that. All right. So far, so good? Well, it's all just definitions and rigmarole theory right now. Let's actually put some of this, into practice. First and foremost, the if statement at the beginning is the essential kicker. All this stuff is beautiful if you can do it, but the main thing is, the condition is if the vector field is conservative. If the vector field is not conservative, everything else is hullabaloo, and you have to go back to evaluating your line integrals this way, which isn't a tedious process, but depending on the curve, it can be a tedious process. But if it's a conservative vector field, then you can take advantage of this fundamental theorem. So how do you test for conservativity? How can you determine if a vector field is conservative? Now we've got 2D vector fields and we've got 3D vector fields. And it's easy for 2D. I don't want to say it's hard for 3D, it's just a little bit more involved, okay? What you need to remember is we're going on the premise that this vector field is conservative, which means it is already the gradient of some little f function. Okay? So here's the potential function. When I take the gradient of it, I have partial with respect to x and partial with respect to y as my two components, okay? Now, let's stop right here. This is the way we know gradient is constructed. Let's say we're now starting with a vector field that we're looking to see if it is conservative. And I'm going to call its I component, I'm just going to call it capital P, where P is a function of x and y. Kind of like the first example, 2x plus y was its I component. And I'm going to call the j component Q. Okay? So now we want to see, is this thing conservative? In other words, does it have this property? Is P some function is partial with x, and is Q some function, that same function is partial with respect to y? Well, the way you can check it is if, well, here's a hint. In case you can't see it. How are those two things related? Second mixed partials. F, little f, scalar function s partial with x then y, and then little f's second partial with y then x.
So
Those are the same. Remember, for any scalar function, this was previous test, this is test 3 stuff. If you take those second mixed partials, those are always the same. And notice, if this thing's conservative, which we're trying to test, then this is already a first partial with x, and this is already a first partial with y. So, if I take this thing's partial with respect to y, which would technically be this done here, and I also take q's partial with respect to x, which if q is the same as this, it becomes that. How should these two things be related? If this is conservative, they should be the same, because you're essentially saying, if you're conservative, you're already a first partial with x and you're already a first partial with y. So when I mix the partials up, take this thing's partial with y and this thing's partial with x, it should give me something equal. So if those are equal, then in 2D you have a conservative vector field. So notice you kind of have to, the way I committed it to memory as a Calc 3 student, I said if P is in the I component, which is the x place of a vector, I guess, the horizontal component, if you take its partial with the other variable, with respect to y, and you take q, which is the j component, which you associate with y, if you take its partial with x, the other variable, if you mix those partials up, then that checks for conservativity. So the previous page, let's go to the one that we've already dealt with. This is the p, and this is the q. If you take p's partial with respect to y, what's it going to give you? Partial derivative with respect to y, which means 2x is a constant and y is your variable. 2x as a derivative would go to 0, 1y would go to 1. So the partial of p with respect to y is 1. The partial derivative with q with respect to x, 1. Yeah, keep in mind you got to mix them up.
Yeah.
So partial with y there is 1, partial with x here is 1. If those partials are equal like this, then you've got the criterion for a conservative vector field. Okay, which means this is some function's gradient. There's some little function f out there that I can sort of back step through this process to and find as the potential
Oh,
function.
I just turned this thing off. I thought I did anyway.
So let's check this one. That's your p, and that's your q. So let me just do it this way. P of xy is the I component, 2xy plus 3. Q of xy is my j component, which is x squared plus 5. And then I want to check for conservativity. So is p's partial with y equal to q's partial with x? Big question mark over the equal sign. So just compare those two partials. P's partial with derivative with respect to y. Keep in mind, x is a constant. So 2x is a coefficient and y goes to 1 here. 3 goes to 0.